understanding of IPv6, the next generation Internet protocol.
What is IPv6?
Introduction of IPv6, the next generation Internet protocol. In the ever-expanding landscape of the Internet, the demand of more IP addresses, improved security, and streamlined network operations has driven the development of the next generation Internet protocol, known as IPv6. So IPv6 or Internet Protocol version 6 represents a fundamental shift on how devices are connected and addressed on the Internet, offering a plethora of advancement over its predecessor or the IPv4. So in plain terms, IPv6 is the new version of Internet Protocol designed to meet the growing needs of the Internet, like more IP addresses, better security, and smoother network operations. It's like an upgrade to ensure there's enough room for all of the devices connecting to the Internet and to make things work more efficiently and securely. Address space exhaustion. One of the primary motivations behind the development of IPv6 was the impending exhaustion of IPv4 address space. With the explosive growth of Internet-connected devices, the finite pool of IPv4 addresses was rapidly depleting, leading to challenges in allocating addresses to new devices and networks. IPv6 addresses these issues by providing an enormous address space capable of accommodating virtually limitless devices and networks. So in plain terms, address space exhaustion is IPv6 was developed because we were running out of IP addresses with IPv4 due to the increasing number of internet connected devices. So IPv6 solves this problem by offering a massive pool of addresses, allowing for a virtually limitless device and networks. Enhanced addressing and routing. IPv6 introduced a new addressing scheme utilizing 128-bit addresses compared to the 32-bit addresses used in IPv4. This expansion in address space allows for a significantly larger of a unique addresses, facilitating more efficient and hierarchical addressing scheme. Additionally, IPv6 simplifies packet processing and routing by streamlining the IP header and eliminating the need for complex address translation mechanisms. So, IPv6 uses longer addresses, the 128 bits compared to 32 bits in IPv4, so allowing for many more unique addresses. This makes addressing more efficient and simplifies routing by making the IP header less complex and eliminating the need for complicated address translation. Improve security. Security is a paramount concern in today's interconnected world, and IPv6 incorporates several features to enhance network security. So IPsec or the Internet Protocol Security is integrated into the IPv6 protocol suite, providing built-in encryption, authentication, and data integrity services. This native support for IPsec enhances the confidentiality and integrity of communications over IPv6 networks, offering the robust security framework without the need for additional overhead. So IPv6 comes with a built-in security features like IPsec, which encrypts, authenticates, and ensures data integrity. This enhances the security of communication over IPv6 networks without adding extra overhead. Stateless auto-configuration. IPv6 introduced stateless address auto-configuration, simplifying the process of configuring network interfaces. Devices can generate their own IPv6 addresses based on network prefixes received from routers, eliminating the need for manual configuration or DHCP servers in many scenarios. This plug-and-play capability streamlines network setup and administrations, particularly in the dynamic and rapidly changing environment. So, IPv6 make it easier to set up network interfaces by allowing devices to generate their own addresses based on information received from routers. So this eliminates the needs for many configuration or DHCP servers, making network setup and administration simpler, especially in dynamic environments. Transition and coexistence. While IPv6 represents the future of Internet addressing, the transition from IPv4 to IPv6 is a gradual process that requires careful planning and implementation. Various transition mechanisms, such as dual stack, tunneling, and translation, enable interoperability and coexistence between IPv4 and IPv6 networks during the migration phase. So these mechanisms ensure a smooth transition while preserving compatibility with existing IPv4 infrastructure and services. So moving from IPv4 to IPv6 is a gradual process, and various transitions mechanisms like dual stack, tunneling, and translation help ensure compatibility and smooth coexistence between IPv4 and IPv6 networks during the translation phase. So these mechanisms make sure that existing IPv4 infrastructure. In short, moving from IPv4 to IPv6 is a gradual process, and various translation mechanisms like dual stack, tunneling, and translation help ensure compatibility and smooth coexistence between IPv4 and IPv6 networks during the translation phase. So these mechanisms make sure that existing IPv4 infrastructure and services remain functional while migrating to IPv6.
IPv6 in binary. IPv6 has 8 hextets as it is converted into binary per character. For example, 1 is equals to 10000 and 0 is equals to 000 and 0 is equals to 000 and 2 is equals to 0100. Each hextet represents 16 bits, resulting a total of 128 bits for the entire IPv6 addresses. Address notation and examples. IPv6 addresses, as mentioned earlier, are expressed in hexadecimal notation. Here's a breakdown of an example IPv6 addresses. Remove continuous zeros and simply replace all the zeros with a double colon.
IPv6 addressing. IPv6 addresses are 128 bits in length, representing a significant expansion over the 32-bit addresses used in IPv4. IPv6 has a 128 bits long. It has 8 sections called hextet 1, 2, 3, 4, 5, 6, 7, 8. IPv6 uses colons to separate hextets rather than using dots.
Types of IPv6 addresses. Unicast addresses. Unicast addresses identify a single interface with the IPv6 network. There are several types of unicast addresses. Global unicast address. Comparable to IPv4 public addresses, global unicast addresses are globally routable and unique across the Internet. Linked local address. Used for communication within the local network segment, linked local addresses are automatically configured and do not require external routing. Unique local address. Addresses are similar to IPv4 private addresses and are used for local communication within a site or organization without being globally routable. Multicast addresses. Multicast addresses identify multiple interfaces or hosts, enabling efficient one-to-many communication. Anycast addresses. Anycast addresses identify multiple interfaces, but data packets are routed to the nearest of several identically configured interfaces. ADCAS is typically used for load balancing and fault tolerance. IPv6 header. The IPv6 header is streamlined compared to its IPv4 counterpart, designed to improve routing efficiency and accommodate new features. Here is an overview of the structure and key fields of the IPv6 header. Structure of IPv6 header. Version 4 bits, traffic class 8 bits, flow level 20 bits, payload length 16 bits, next header 8 bits, hop limit 8 bits, source address 128 bits, destination address 128 bits.
Translation mechanism. Translation mechanism have dual stack. So a dual stack running IPv4 and IPv6 simultaneously allow for a gradual transition, enabling communication between devices using neither protocols. So, tunneling. Tunneling is involved in encapsulating IPv6 packets within IPv4 packets, facilitating communication across IPv4-only network of infrastructure. And last is translation. So a translation is mechanism map between IPv4 and IPv6 addresses, enabling communication between devices using different protocols. IPv6 deployment strategies have phased approach. Implementation IPv6 deployment in planned stage, ensuring smooth integrations with existing infrastructure and minimize disruption. Network readiness assessment. Assessing network readiness helps identify potential challenges and ensuring that infrastructure and devices are compatible with IPv6. And last is addressing integration challenges. Addressing challenges such as compatibility issues, security concern, and the needs of staff training is essential for a successful IPv6 deployment.
So, the next is IPv6 adoptions and trends. The first is the global adoption statistics. Global adoption statistics is providing insights into IPv6 adoption rates worldwide, helps understand the progress and challenges in transitioning to IPv6. Second is the industry trends and best practices. Exploring industry trends and best practices offers guidance for organizations planning IPv6 deployment and integration. The third is the case studies of successful IPv6 deployments. Examining case studies of organizations that have successfully implemented IPv6 provides valuable lessons and insights for others.